All right, so we get to keep talking about attention today, and we're getting to, in my opinion, probably the climax of the course, and really what a lot of the deep learning research of the last decade has culminated in, and that is transformers. So yeah, so today we'll start off with reviewing what we ended on last time, which is normal attention, just basic attention on an RNN. So take a second to turn to the person next to you and see if you can explain how we got this, what we will call a context vector, CT, and why it is better than a normal RNN, better than the context vector for a normal RNN. All right. Can I get a volunteer to try to take a shot at explaining how we get this context vector, CT, and why it might be better than the context vector for a normal RNN? Heard some conversation. I had to be talking about something. Who doesn't know? All right, Johnny, let's work with you. Let's see if we can get to a point where Johnny understands and go from there. So, Johnny, if you were to take a shot, like just stab in the dark, how do we start off with, how do we get this context vector? That is pretty much 100% true. So it is totally a node in, yeah, the CT are activations, so it's not weights, and it is a weighted combination of previous outputs. The one slight difference is that the attention weights that we use to get it are not learned parameters. Instead, they are what we would call attention weights between our current time step and all of the previous time steps. So yeah, Brendan asked, what does that mean? Why might that be useful? So I'll remind you that the reason why attention was introduced was because of this long-term memorization problem where you had to, if you were doing sequences of 2,000 words, in order to predict the 2001th word, we have to squish information from all of the previous 2,000 tokens into a single vector. However, with attention, we can just store the representations of each of those previous tokens, and then compare those representations, compare those activations to the token that we currently need to decode. And so basically, to sum all that up, instead of basically this vector, the CT vector being a sum of all the previous vectors, it is a weighted sum of the previous vectors based on attention weights between the current vector and each of those previous vectors. Yeah, Drake. Yeah, so dot product is one. I think that's a great way to that's a good baseline kind of assumption. Like you can just think of it as a dot product. There are other ways that people do it, But yeah, you can, for now, I think a dot product is a great way to think of how we get these ATs. So to clarify, this is a dot product between the current vector and each of the previous vectors. And so we will have, in this case, 4 attention weights based on the dot product between this red vector and each of those 4 previous blue vectors. Okay, yeah, question. How does this differ from the memory gates in an LSTM? So great question. That is a question to ask. So in the memory gates in an LSTM, we're basically adding and subtracting information to a single vector. Whereas and in this case, we're still doing that. So that is still happening along this path from left to right. However, when we use attention, we don't have to rely only on this last block in order to predict the next token. We can rely on any of the previous blocks because we don't have to store it in a single vector. Yeah, question. Exactly. Yeah. So there are a couple. You hit on exactly the two main benefits. One, we don't have to squish all of these into a single representation, and 2, we can have different weights based on the current token that we need to predict. If you remember, for normal RNNs, we didn't have a choice in what we got. We got what we got, and it was a summary of all the previous information, and we had to make do with that in order to predict the next token. In attention, we can basically choose what that weighted combination is to be more relevant to the current token that we want to predict. You still have a question? So the attention is still a summary, but it is dependent on the current token. The current token that we have to predict. Because these attention weights, and this is not clear in this diagram, but these attention weights depend on both this current red vector and each of these other vectors. And the attention weights are, you can think of them as the dot product between the current vector and each of the previous vectors. So we take the dot product between red and token 4, and that gives us a single number. We take the dot product between red and token 3, and that gives us a single number, et cetera, and then we just take that weight that we got from the dot product and multiply it by that vector in order to get this CT, which is a weighted combination of them. Okay, yeah, Brandon. So then, no, so the red tokens just correspond to the decoder. And so if we unrolled this a couple more times, we would have more red. So the color is not super significant here. Yeah, question. So good question. So we're not concatenating. We are taking A1 times V1 plus A2 times V2 plus A3 times V3 plus A4 times V4. We are adding them. Yep. All right. Yeah, question. Exactly. Yeah, and you're bringing up a really good point. So yeah, these attention weights will be different for this current token than for subsequent tokens. Why is that? Why will they be different? Exactly, totally. And yeah, that's a great, and I think it's even more, I think that's an even better example if we're talking about a language where you have gendered articles, right? Like if we're talking about Spanish, el carro, like it would be helpful in this case. Yeah, looking at el would be helpful for carro, but probably not for any other word after that. And Yeah, exactly. Yeah. So that's a great point. So as we go along longer, we will have more previous vectors to look at. And so this A vector will become longer because we're going to be taking a weighted combination of more of a longer context. Yeah, question. Good question. Yeah. So in a normal LSTM, you're totally right. We would just discard these previous intermediate states. Whereas for attention, we need to hold on to these so that we can perform that dot product and do attention on them. So that is a good. That's a good point. There is an increased memory requirement. Well, actually, I'm gonna walk that back because we already have to store those, right? We have to store our activations on the forward pass anyways in order to do back propagation. So really, there isn't any extra overhead to storing those, at least during training. Great question. So the question is, if you don't learn the attention weights, how do you get them? And you can think of them as they are kind of like implicitly learned, because this the current hidden state is going to be the output of a hidden layer. And so it does depend on our neural network parameters. And so our neural network parameters will make this vector whatever it needs to be in order to get good attention weights. I think let's pause on this diagram for now and look at a couple of examples, because I think the more examples we see of this will help us flesh out the idea of attention a little bit better. Okay, so yeah, so we then take this context vector, use it to predict the next hidden state, and so on. Now this is what we will call an attention matrix. And so here we have a translation task, and we're translating from French to English. And you can see that, and the colors in this attention matrix correspond to the weight correspond to the magnitude of attention weights between the token we are predicting and each of the tokens that preceded it. Okay, so we take as input l'accord sur la zone économique européenne a été signé en août 1992.end. Okay, I butchered that, I know. So then we have all of that, and we have all of our hidden states from that, and we want to predict the word the. And so you can see, what does it pay attention to? Le, which makes sense, right? Okay, so let's go to the next one, agreement. What are we paying attention to? Accord. On is paying attention to sur, the, la. And then, oh, wait, this is kind of interesting. So European is not paying attention very much to the next word. So up to here, we were just looking at the words in the same positions. But what is European looking at in the previous hidden states? European, yeah. So what was that? But the order is different, exactly. Yeah, because in French, you have this kind of reverse syntax where you have noun, adjective, adverb, or adjective, adjective. Yeah. Yeah, and so then you see économique corresponds to economic, and then and then area corresponds to zone. So there are a couple of kind of useful things that come out of using attention that are helpful in addition to this memorization problem. Attention-based neural networks are very interpretable because we can literally see where the network is looking and paying attention to in the previous sequence. Another example of this from my research, there's a problem in chemistry where you are trying to predict the products of a chemical reaction from the reactants. And so these researchers trained a neural network to translate from reactants to products. And a significant problem in that process is knowing which atom in your product molecules corresponds to which atom in your reactants. And what they did was they looked at the attention weights between each of the product atoms and each of the reactant atoms. And those attention weights basically told them exactly which atom was being mapped. Which atom in the reactants corresponded to which atom in the products. So yeah, there's some really useful properties that arise from these attention-based networks. Yeah. So let's go back here. So this is still retrospective because these basically, we already have hidden states for all of these French words. And so all of the English words come after the French words. And so each of the English words is still looking backwards. There's no looking forwards here. Well, no, it can. Yeah, and in fact, that happens. So European is looking ahead in like European in French was like the 7th token and it was the 5th token here. So it can look ahead, like I think we need to be clear what we're talking about by like looking ahead, because like we're still looking backwards at 1992 because we already have hidden states for all of the French words. And then we start decoding the English. Right. Yeah. Well, so yeah, so first of all, in this case, we are assuming that I understand what you're asking. So in this diagram, let's say N1 is the number of French words and N2 is the number of English words. Then there are N1 blue vectors and N2 red vectors, okay? And each of the N2 red vectors can look at all of the N1 blue vectors and nothing else. There are variations where we also allow it to look at other of the red vectors, other of the tokens we're decoding. But in this case, in this diagram, we're just only letting our translation look at the French input. Okay. All right. So this is architecture called NMT, Neural Machine Translation from Google, that uses bidirectional LSTMs with attention. So let's try to unpack what's happening here. So here we have an encoder LSTM and a decoder LSTM. And so we will apply the encoder LSTM to our, let's say, French input, and then try to decode an English output. What we're going to do is we're going to stack several bidirectional LSTM blocks. So that's represented by this dashed rectangle with the green and the pink nodes inside. You can see we're looking at the input sequence from both directions, left to right as well as right to left. And then the hidden states that we get from there will be fed into another LSTM, another bidirectional LSTM block. Actually, never mind. It looks like only the first block is bidirectional, and then all subsequent blocks are unidirectional because we already have that bidirectional context. Okay, so we take those and then we finally summarize, we finally store each of a hidden state for each of the tokens in the input sequence. And that's that is represented by this gray box. So this gray box contains hidden states for each token in the French input sequence. Any questions on that so far? Okay, and then we have to do attention somehow. And this will be our attention function. So this is how we are going to get our attention weights between each of our decoding tokens and all of the input tokens. And so I said dot product. In this case, it is not a dot product. In this case, it's this attention function, which is a feed forward neural network with one hidden layer. So basically, we have a single layer neural network. A single hidden layer that takes as input the current token to decode xt, as well as, the current token to decode yi-1, and one of the previous hidden states xt. So our xt's will range from 1 to m, so x1, x2, all the way to xm. And we're going to apply this attention function, which you can think of basically as a weighted dot product between the current token to decode and each of those hidden states. Does it make sense how in this case we're using a weighted combination instead of a dot product? Okay, and then this will take those, so we will get ST for each of our hidden states, which are attention weights, and then we will apply this softmax function to them to turn them into probabilities. So they're now all positive and they all sum to 1. Okay, and then we will let AI, which is the context vector for the current ith token to decode, and that will be a weighted sum of these hidden states based on these probability weights that we got from our attention function. And that is what this blue box is right here. This blue box right here is A1 and is being used to predict Y1. And so to do that, we have another LSTM, and this one is unidirectional because we're decoding left to right. And yeah, this context vector is then fed in at every layer of this 8-layer LSTM in order to predict the next token. Yeah, that's complicated. So to sum up all the things that go into this NMT network, we have bidirectional LSTM. We have multi-layer LSTM, where we have multiple LSTM layers stacked on top of each other. And we have attention. Those are kind of the 3 main things here. Okay, yeah, question. That attention function is learnable. It is parameterized by a weight matrix. Yep. Hey, yeah, question. Yeah, so that's not the best representation. I don't think this gray bar represents x1, x2, all the way to xm. So there are multiple hidden states in that gray bar at the top. So the decoder takes as input a weighted combination of information from this gray bar. Does that make sense? Okay. All right, let's look at some more examples. Oh, we're not going to look at more examples until the next lecture. But yeah, this is not the last time you will see attention, so it's okay if it doesn't 100% make sense quite yet. But yeah, with that said, any questions on attention? All right. Okay, so now we have embeddings, word embeddings. So word embeddings answer the question, how do we represent the meaning of a word, and how can we use that representation? So if you were to turn the word pizza into a vector of numbers, what's some way that you might do that? Just off the cuffs. What's a way that you could turn the word pizza into a list of numbers? Yeah, question or idea. Yeah, so if you have the vocabulary of all the words you want to consider, like 20,000 words in the English language, just have a 20,000, a vector of length 20,000, and have entries in 0 as all the spots, and then 1 in the location corresponding to pizza. That's an idea. Yeah. What else? What do you think? Totally. Yeah. So we would call that a bag of letters. So yeah, you instead of having a length 20,000 vector, go on a token level. We only have 26 letters, and yeah, have a 1 in each slot if that token appears in the word. Totally. Yeah. What else? Yeah, Brendan. You could have various images stored of pizza. Yeah, so first of all, you'd have to have a database that links the word pizza to images. And then yeah, you could use like a CNN feature extractor and sum up all the features of all the pizzas. That is one way you could do it. Yeah, Boris, what do you think? Oh, that's an interesting idea. Grab a number of words associated with pizza. Interesting. So then, yeah, explain to me that idea a little more. Yeah, I really like that idea. So Boris is getting at a very interesting idea of looking at the context around a word to describe that word. And so yeah, we might scan over Wikipedia, look at every time that the word pizza occurs, take a window of 5 words on either side of the word pizza, and then yeah, like let pizza be represented by basically a sum of the one-hot encodings of all the words on either side of it. That's a really interesting idea. Okay. So this is one question that we can ask of word embeddings. How similar is pizza to pasta? How related is pizza to Italy? And so the question is, can we discover these similarities by using the right word representation? So this is the this is the one-hot encoding idea, where we have a vector that has length of our entire vocabulary. It doesn't include any context information. We could also have a bag of words context, like Forrest described, where you include contextual information. We're going to talk about word embeddings. So these are not one-hot vectors. They are fixed length vectors. And so it has the benefit of this vector doesn't grow with the size of your vocabulary. And yeah, you can think of the dimensions of this vector corresponding to different features that describe that word. So in the end result, if our word vector had length 2, where you have x and y, this might be kind of what our desired word vectors would look like. Hopefully bus, car, and train would be kind of clustered in a similar spot. Apple, orange, banana would be related. And then, yeah, looks like, yeah, if you were to look at this, what would the y-axis represent? Like organic versus not organic, foodness versus transportationness. Yeah. And then if we were going to go left to right, or on the x-axis, what might that represent? Solid versus liquid, but also we have some. So yeah, I think we're already discovering color was an idea. I think we're already discovering that we would like some more axes to be able to divide these words on, right? And so we're going to make these word vectors somewhere between 100 and 300 dimensions, where each axis represents a different axis of variation for different words. And after learning, we can do some really cool things with these word vectors. For example, we might see that there is a vector that if we do vector subtraction, we see that there is a vector that represents the relationship between man and woman. And it so happens that that vector is the same vector that represents the relationship between uncle and aunt, and also king and queen. And if we take that one step further, we can, there's also a vector that represents the relationship between king and kings, queen and queens. And so you can imagine doing like multiple layers of arithmetic with these vectors, where you take the vector king and you subtract the vector for man, add the vector for woman, and the nearest vector to this sum of vectors happens to be the vector for queen. And these are properties that arise just from unsupervised training of these word embeddings. And so you can use these word embeddings to do analogical reasoning, which is kind of an amazing idea when you realize that these models that are just trained on raw text manage to learn these real world relationships. Yeah, idea or question. What is the algorithm? That is a great question. We're almost there. So a couple of other examples of this analogical reasoning. So we're going to start with a known relationship, France to Paris. And we want to know, suppose we want to know what is the capital of a state. Well, we take the word vector between France and Paris, and we add it to Florida. So we do France minus Paris plus Florida, and we get Tallahassee. Or apply that to Italy, Japan, and you can see that we can kind of use these word embeddings to mine relations between words. Similar for big, bigger, small, larger, cold, colder, quick, quicker. So there's an axis for magnitude. Einstein scientist, Messi midfielder, Mozart violinist, Picasso painter. I mean, Mozart was many things, but they had to pick one word, right? And so apparently violinist was the word that best described him. Although I don't know, I would say that's probably a failure mode, because Mozart was probably known better as a composer than as a violinist. So yeah, I mean, these embeddings are not perfect. But you can see, yeah, again, we have Microsoft Ballmer. So that's Steve Ballmer. He was the CEO of Microsoft. And then we get Google, Yahoo, IBM, McNeely, Apple, Jobs. So again, apparently Yahoo is the CEO of Google. So yeah, they aren't perfect, but in general, they tend to do pretty well with these analogical reasoning tasks. More analogies. More vector addition and subtraction. Any questions or comments on this idea of arithmetic with word vectors or analogical reasoning? Yeah. Totally. Yeah. So you're thinking along the right lines. Like, okay, yeah, we can use these to do like to complete these analogies, but like, are there other ways that we can use these word vectors? In fact, let's, since you asked the question, we're going to skip over the algorithm for now and answer your question. Applications of word vectors. So so we can do word similarity, which is pretty similar to this analogical reasoning stuff, but you can do you can compute the similarity between word vectors. How do you think you do that? With what mathematical operation? Dot product. I'd say that's a pretty good idea for computing similarity between vectors. And so yeah, you could do that to find similar words like thesaurus lookup. Also, you can use them to yeah, try to find phrases that are semantically similar. So in this case, we take the word embeddings for 4 different words in a sentence, sum them up, and then look at the correlation of, let's see. Actually, I'm not exactly sure how we get the numbers in this square. But I'm guessing it is some sort of similarity. But yeah, so I think what they do is they take the 4 word embedding vectors, they sum them up, and then they take the dot product between the sentence embeddings, and we look at the magnitude of the dot products between the sentence embeddings. And you can see that that this first sentence is related to the second sentence pretty strongly. And obviously all of the sentences are related to themselves. That's the dark diagonal. And then these last 2 sentences are also related to each other, which you can see in the bottom right corner of that similarity matrix. Another interesting idea is machine translation. So you can imagine training one of these word embedding models on an English data set and on a Japanese data set, and then trying to align, you use certain vectors as key points, and then you align those vectors with each other. You find like a translation and a rotation that will align certain important vectors with each other. And then from there, you can basically do nearest, if you want to know the translation of a word from English to Japanese, you find basically the nearest Japanese neighbor of an English word in that space. Does that kind of make sense? You can also use them for downstream tasks. And I would say this is how they're used most often. So for example, named entity recognition is recognizing, basically mapping text to a certain concept. And then also part of speech tagging, mapping a word to the part of speech. It turns out that if you use these embeddings, instead of just using a one-hot vector, you end up doing a lot better on these downstream tasks, because rather than just representing a single number in a vector, these higher dimensional vectors like basically include similar information about similar words as well. Relation extraction, this is the analogical stuff. But you can also use this to create knowledge graphs between different words, which you can think of being pretty useful for, basically extracting common sense knowledge from word embeddings. Sentiment analysis is another downstream task. You train sentiment analysis classifier on word embeddings, and it does better than if you just do it on one hot encoded words. Co-reference resolution, that's related to named entity recognition, clustering, similar words, semantic analysis of documents. So the answer is there are a lot of applications. Yeah. So to end today, we are going to talk about the algorithms that we use to get these word vectors. Okay, so yeah, how do we find these magical vectors that have these amazing relationships inside them? So there are several algorithms that you can use to do this that people have come up with. One of the first algorithm to popularize this was called word2vec, and it has various models and various ways to train it. But we're going to talk today about the skip-gram model and the negative sampling training method. So this is how it works. We want to figure out an embedding for this word, wampanoag. And so to do that, we are going to look at its context. We're going to look in a window of size 5, and we see those other words on either side of it. And so what we're going to do is we're going to learn this matrix W, which is a VW by D. Any ideas what VW and D might represent? Yeah, what do you think? Yeah. Exactly, yeah. So D is the dimension of the embedding space, and V is the size of our vocabulary. And so each word in our vocabulary will get a D-dimensional vector. And we're going to find the vector for wampanoag. And so the way that the negative sampling works, or that skip-gram works, is we're also going to have another matrix, VC, which gives us the embedding for the context of our word. And our training objective will be to maximize just a simple sigmoid function, a sigmoid activation function of W dot product, the dot product of W with C. So basically, we want each word to be similar to the context where it appears. And so as we maximize that very simple objective, it gives rise to these word embeddings. This is very similar to Forrest's idea, where we are looking at the words around it. And yeah, the result is when we train with this objective, we get these really helpful word embeddings that have these relational properties to each other. Any questions on the SGNS algorithm? Yeah. Mm-hmm. Great question. So yeah, so first of all, these are going to be normalized. So that's one constraint on that. So the question is whether whether the easiest way to maximize this would just be to increase the magnitude of these vectors. That's pretty easily remedied by controlling, by normalizing them. However, what I thought you were going to say is, isn't there a trivial solution to this where we basically learn the same vector for everything, right? If we learn the same vector for everything, then that will maximize that objective. That's why we need negative sampling. So what we do for that is we hallucinate a context. We take random other vectors, and we want random other words, Australia Cyber the 1985, and we're going to create a context vector out of those words. We want to minimize the dot product of W with that wrong context as we maximize the dot product of W with that true context. Yeah, Dane. Great question. Is there a constraint that the hallucinated values do not include values from the true set? I don't know. But I think if your vocabulary is 20,000 words, then you're probably like the number of times that randomly sampling 5 words out of 20,000, the amount of times that collides with your true context is probably negligible enough that it really doesn't play a factor in training. So maybe, but I don't think it would matter. Okay, so that is skip grams with negative sample.